Hello, my name is Clément Escoffier. I'm Principal Architect at Red Hat, and today I'm going to present how we can bring Reactive to enterprise developers. And if you think about it, enterprise developer and reactive developers are really different personas. They are using different constructs, different code style, different software engineering practices. On the enterprise side, it's more imperative code, synchronous, sometimes blocking, where you have transaction, where you are using a Hibernate to access database and such kind of things. You have dependency injections and so on. On the reactive side, it's more event-driven, it's more functional, it's all about being non-blocking, all about reacting to events and stimuli. So how can we reconcile both sides? Unification of reactive and imperative is one of the core pillars of Quarkus, and that's what we are going to see today. But first, what is reactive? What does that mean for you, for an enterprise developer, and do we really need it? So if you look at the Oxford Dictionary, you will find this definition. Being reactive means showing a response to a stimulus. Okay, there is a sub-definition which is quite interesting too, which means that being reactive is about acting in response to a situation rather than creating and controlling it. If we take those two definitions and we apply them to software, we can write something like this. A reactive software is an application reacting to stimuli such as user inputs, messages, and failures. All those stimuli are outside of the control of the application, so you are really acting in response to them and not necessarily creating them. But if you think about it, this is the nature of software, reacting to user input and things like that. So reactive is not new at all. Reactive comes from the roots of software coming from the 60s. But what does that really mean today? Well, if we take this definition, we can consider that reactive and event-driven are really close, because an event-driven application is an application that will receive events and emits events. And yes, it's right. Reactive and event-driven are kind of close, but a reactive application is going to ingest events, signals, failures, and so on. So what's really new behind it? Because you can do that using well-known enterprise constructs such as AGBs, message-driven beans, or CDI observers. Well, it's all about the concurrency. And concurrency means the number of events you will be able to process at the same time. Reactive is about building highly concurrent applications, using non-blocking asynchronous I/O, using reactive streams to handle back pressure, to handle such kind of things, to push and pull, and also using reactive programming to help you doing such kind of things. This new level of concurrency will let you ingest more, handle more, and using efficiently the resources that are given to your applications. And this is actually key in the cloud, where the resources that are given to your applications are really low in comparison to good old app servers on mainframes. The thing is, we are not actually building one event-driven application these days. Whether or not you are embracing microservices, serverless, and so on, most of the time you are building distributed systems. So we want to apply the reactive definition not only to a single node, but to the whole systems, and saying that all the system is going to react to messages, to stimuli, that they are not necessarily controlling it, and trying to have your logic emerge from these messages. However, one thing we know about distributed systems is that they fail. There is no better definition of the distributed system than this one from Leslie Lamport that just says that, well, it's going to fail. You can be a genius and building a distributed system. Failure is part of the game. And we need to take that into account, because on the cloud, in a container, or even in any type of applications or modern applications, failures is as usual as a correct outcome. So reactive is not only about high concurrency, it's also about building better systems that embrace failures and react to them gracefully. How does that work is by applying reactive to distributed systems, we are defining a new architectural styles that we will name reactive systems. These reactive systems are based on elasticity pattern, resilience pattern, and the core elements, the essence of the systems, is exchanging messages. But you can say, well, I'm doing microservices, or I was doing HTTP services for years, and there is nothing wrong with that. Where we start really seeing the limits with HTTP, because when you think about it, HTTP is about strong coupling, while microservices is about loose coupling, where any of these elements can evolve at any time. And HTTP doesn't really work that way. Let me explain why. Well, there is some kind of uptime coupling, in the sense that if one of my microservices or one of my applications fail, then the caller is going to fail, and the caller is going to fail, and it cascades the failures until you get the users, get out of 500 response, and that's an unhappy users, and you really want to have happy users. So we need to find another way of doing this. And you can say, well, circuit breakers. We can isolate the failures and avoid the cascade by using a circuit breaker. And I say, yes, circuit breakers are great. They are great. They are monitoring an interaction between two microservices and decide, according to the number of failures, according to timeouts and things like that, if the service must be called or fallback must be called. Now think about it. Imagine that you are interacting with your bank and you want to know your balance. Unfortunately, the balance service is unavailable. What kind of fallback would make sense in that case? That doesn't make sense, right? So sometimes using fallback doesn't work. And also, circuit breakers are not being designed for the dynamic nature of the cloud, because timeouts and the number of failures may likely depend on how many instances of your service are executed, are instantiated at that time. How many instances can you rely on? And this number of instances may change, and actually even the location of those instances may change over time. So everything about timeouts and number of failures is likely going to be adapted over time of your application, and circuit breakers are not really good with this. Also, tuning a circuit breaker is very, very complicated. There is thread pools, there is a lot of various settings that you need to customize to make really good usage for them. So what can we use? Well, since probably the 80s or something like that, there is another trend, another way to interact, which is not synchronous, that will use middleware that will separate all our entities, and that's messaging. With messaging, you can send messages to virtual addresses. So you're never calling directly someone, you are sending that to a virtual address, and you don't know if there is one consumer, n consumer, or even zero consumer, because you may have durability of your messages, and they will be processed when one consumer will be there. Modern messaging systems use non-blocking message passing. You can even have request replies, there is no problem with that. And resilience is managed by two ways. One, you can have multiple consumers, as I said, so if one failed, another one can still manage the message, incoming message. And you also have acknowledgement support that will let you retry or have very fancy way to handle the failures. When you apply messages and asynchronous messages to a distributed systems, you implement reactive systems. And a reactive systems is a system using asynchronous message passing, and thanks to this, it will enable elasticity and resilience. Elasticity because the number of consumers can evolve over time, and resilience because you have all the acknowledgements and multiple consumers support. If you are able to handle messages even under fluctuating load, and even when facing failures, you become responsive. So you have built a better distributed system. And reactive is really about this, building better distributed systems. And one of the key aspects is that your asynchronous message passing must use asynchronous non-blocking message passing. The non-blocking is key, because if you are not non-blocking, you will lead to a lot of threads which will use a lot of memory and you will be very inefficient. And that's probably one of the key aspects of reactive. Reactive means being asynchronous, and being asynchronous doesn't mean multi-threads. Being asynchronous means never ever block. That means using non-blocking I/O and having a way to write code that is never blocking, so more asynchronous code. So let's now ask a few questions and try to see how an enterprise developers can start using reactive. So the first thing we are going to see is completion stage. Completion stage is a type that is provided by the JDK to handle asynchronous result, asynchronous computation. With completion stage, you enqueue some computation and you will be called when this computation completes with the result. And you can change those computation. There is several issues with completion stage. Typically, the API is not necessarily user-friendly and is very different from the rest of the JDK. So for developers that have never used them, it's kind of weird. Second thing is that completion stage are eager in the sense that as soon as you enqueue the execution, it's already started. So to avoid these two issues, we strongly recommend to not use completion stage, but to use Uni. Uni comes from Mutiny, which is a new modern navigable reactive programming library. We're going to see a bunch of examples using Mutiny in this presentation. But what you need to know about Uni is that it's just a structure, an asynchronous structure that will be completed when the result is ready. And then you can chain your call, you can do composition and things like that. So what does that mean for an enterprise developer? Well, let's take the first example. If you want to implement a REST API, based on HTTP. Again here, instead of returning a completion stage, you will return a Uni. And what will happen in that case is the method is going to be called, but because it's asynchronous, the thread is going to be released. It can handle some other calls. And what is interesting here is that it will continue the computation only when this Uni here is completed. And when it gets completed, the response is returned to the client. So it's very easy to use. You just change your result and have to return Unis. If you call HTTP microservices, even if we discussed about HTTP, they are still widely popular, then we strongly recommend to use MicroProfile REST client, which will map an HTTP API to a Java interface. So it's much simpler to use from your Java applications because you don't have to use a raw, low-level HTTP client. So for each method from your Java interface, you will use a notation to indicate how the HTTP request need to be emitted and how the result need to be read. Here, for the same reason, we are going to return a Uni in the sense that we are going to call the service, the remote service, and of course it's asynchronous. Of course, it's going through the network and so on. So it's very important to use an asynchronous result here and to not block the thread waiting for an answer. And your Uni will get the result as soon as the HTTP response arrives and is processed, and then you can continue your computation. But what about streams? Because so far we have seen Uni, and Uni is for 0 and 1 items. Well, in Mutiny, we have two types. We have Uni for 0 and 1 items. It's lazy, following a subscription pattern, so the computation doesn't start until someone is interested by the result, like you have in Java util streams, and so on. And it has a set of operators to chain and compose your operations. On the other side, we have multi. Multi is for all to potentially an infinite number of items. It's also lazy, using subscription patterns. It has operators, the same set the operators for Uni, plus a set of operators dedicated to multi-items management and handling, and it has back pressure. Uni doesn't necessarily need back pressure because you get only 0 and 1 result, so that means that the subscription, the fact that you are interested by the result, is enough to say that you are ready to handle this result. So, but what is back pressure? As soon as you are handling with data streams, you have the issue with fast producer and slow consumers. If you don't have any back pressure, then the fast producer is going to send way too much data to your slow consumers, and your slow consumers will start buffering them until you reach out of memory. Back pressure is about making or using a protocol between the consumers and the producers to be sure that the consumers get never out of memory. So how it works, there is several protocols, there is several way or mechanism to do that, but one of the way that is the most popular in the Java world these days is reactive streams. And with reactive streams, the slow consumers will tell the fast producers how many items it can handle. So it starts, it subscribes to the producer and say, okay, give me 2. And once you get the 2, you can say, oh, give me another 2, and so on. So you end-to-end communication, your end-to-end pipeline get adjusted, the pace, the velocity get adjusted by the consumers to be sure that you are not flooding any part of your system. So it's very important, especially in terms of resilience, and to be sure that you never crash. So multi has back pressure built in, and it's actually using reactive streams protocol, so the protocol we just explained. And the only difference with Uni is that you will return a multi, and a multi has several items, maybe empty, but maybe an infinite number of items. In this first example here, we have a multi of string that will contain a set of items which will be greetings messages. Here, it's again a JAX serverless endpoint, and we will write the result into a JSON array, which means that as soon as we get some result from the greeting service, we can start pushing that to the client, and once the stream is completed, we can just close the array. This second example uses SSC, and here we have an infinite number of greetings. So server sent event lets you push data to your consumers using a stream based on HTTP. And here again, you just return a multi, you set what kind of types, how do you want to encode those items, and you're done. So it's very simple. The question is, how do I get those units? How do I get those multis? But before answering this, we need to answer another question first. You probably heard a lot about Kafka. Kafka is widely popular, it's a great platform. But a lot of people ask me, does using Kafka make me reactive? I don't want to spoil the rest of the presentation, but the quick answer is no. You need to use Kafka correctly to be reactive, and it's what we are going to see now. So, Quarkus is not only for HTTP, it can do messaging and streaming. But as soon as you discuss messaging and streaming with enterprise developers and Java enterprise developers, they immediately think about GMS, message-driven beans, and yeah, they're not very happy about that, and I can completely understand. These APIs are not really aged well, so we need something a little bit new, a little bit more integrated in a CDI model, in a modern development model. And that's what we do with MicroProfile Reactive Messaging. And with MicroProfile Reactive Messaging that is integrated in Quarkus, we will make messaging as easy as possible. The goal is to make the development of event-driven microservices as easy as HTTP microservices. Reactive messaging lets you connect to a bunch of messaging middleware, AMQP, Kafka, RabbitMQ, MQTT, and so on, and handle the communications. So how does that work? To see how does that work, we're going to see a demo, and this demo is about coffee shops. In traditional coffee shops, you go to the bartender, you ask for your coffee, you get to the coffee machine, get your coffee, but you're waiting, and during that time, other customers are queuing. So we are really in the imperative blocking way. There is a new type of coffee shops where you go to the bartender, you order your beverage, your coffee, and you pay, and they tell you, oh, you need to wait over there. Okay. In the meantime, they write your name, they misspell it, that's part of the brand. And then you go there and wait for your beverage. And during that time, during you waiting, other customers can be handled by the bartender. Then the barista gets your order and can start preparing it, and then you get your order. The only difference with this well-known chain of coffee shops is that I have implemented a dashboard to know in which state is my order, if it's getting prepared, if it's ready, and so on. So let's see this in action now. Remember, we have three microservices: the coffee shop, HTTP barista, and Kafka barista. This is the code of the coffee shop microservice. If you look carefully, you will see that it's actually a Spring controller, because in Quarkus you can use the Spring interrupt layer to build reactive applications, even using the Spring model, the Spring APIs. So what we do here for the HTTP route is that we use a REST client to invoke the HTTP baristas, and we do this asynchronously because look, I'm returning a uni here. If we look at the barista service, this is a REST client that is going to map this call, the call to orders, to an HTTP invocation, but it's easy for you because you don't have to use the raw low-level HTTP clients. Let's now look at the messaging part. The messaging part is handled by this method here, but before looking at this method, we need to explain those emitters here. We are going to deal with channels, and channels is a concept from MicroProfile reactive messaging, and channels will be mapped later to Kafka topics, to MQP addresses, to MQTT topics, and so on, even in memory if you need to do multi-hop processing. So we have two emitters that will let our method send messages to our channels. The first emitter is going to send to the channel sorter, the second emitter is going to send to the queue channels. And then we have this messaging method here that will use those emitters and send those messages. Those channels are mapped to Kafka using a configuration file where here we say that it's Kafka and we set the serializer and deserializer and so on. If we now look at the Kafka barista, so it's another microservice, we want to read from orders and want to write to queue, and in between do this. So we receive our orders, we do the preparations. I'm queuing everything on a single thread executor to illustrate that a barista cannot prepare two things at the same time. Let's now switch to the actual demo. Here is my dashboard. I can order from my dashboard and see my orders here. This is my HTTP barista. This is my Kafka baristas. So if I enter my name and I order frappuccinos, first I cannot order more than once because, well, it's blocking. So I cannot call another one. And as soon as this one dies, then I get an error here because obviously it's HTTP. So the error cascades to the caller, and that's not good. So if now I start using messaging and I want to order chai, for example, messaging, I can order several ones and they will be processed one by one by a barista named Mia. So if I order a lot of them, you can quickly see that Mia cannot handle the load, so I may be able to start a second baristas, and as soon as the second baristas get ready, it will start to process others' order. Let's get some more. Oh, Freddy. Freddy is now ordering a few of these orders that were pending. But one thing that is also interesting in microservices is when we have no consumers. I can continue ordering, let's say, latte, and instead of losing my orders, they will be just queued, and as soon as one barista get back, it will start processing those orders. So here Julie is now preparing all the pending orders. So what we have seen here is that we have seen that thanks to messaging, we can actually handle more load by starting another consumers dynamically. And even if we have a failure or no consumers, the requests, the orders are not lost because of the durability provided by Kafka or by your messaging systems, and you can recover nicely and gracefully. So in this demo, we have seen how easy it is to implement a reactive systems, but we didn't really cover the reactive streams part. Actually, it's all hidden. When we start emitting messages using our emitters, it's actually a reactive streams that is created. And these reactive streams go all the way to our second microservice and back. So the back pressure is handled by reactive messaging, by Quarkus, without having the developer to be aware of it. What we have seen in this session is how Quarkus make it easy for enterprise developers to embrace reactive. They can stay on the imperative side, they can switch to the reactive side, they can mix all together, they can use what works best for the task at hand. So this unification of imperative and reactive is one of the core pillars of Quarkus. This is only possible because behind the scene there is a reactive engine. This reactive engine is based on Eclipse Vertex and Netty. All the IOs that we have done today are going through these reactive engines. The HTTP request that was arriving are handled by an HTTP server, which is a Vertex HTTP server, so fully reactive and unblocking. And then the request is dispatched to Servlet, JAX-RS, Spring Controller, and so on. Even when we were dealing with messages, it was going through Vertex. When we were sending our messages to the emitters and these channels is mapped to Kafka, it's a Vertex Kafka client that will handle these messages and write that to Kafka. Something on the reception side, it's a Vertex Kafka client that gets this message, call your processing, and back. So the unification of reactive and imperative is only possible because we have this reactive core. You can handle imperative on top of a reactive core. You cannot handle reactive on top of a imperative and blocking core. If you want to know more about Quarkus, about reactive in Quarkus, and how we ease the development of event-driven microservices, streaming applications, and even reactive applications with Quarkus, check our website, which is quarkus.io. You can also interact with the team on Zulip. So you click on this second link here, and you can go to the GitHub repositories, start it, or follow us on Twitter.